Good morning. Today we're talking about graphing motion, and we're looking at distance time graphs. We started this on Friday when we had different people in the class performing a motion. We timed them. Those of you at home, you looked at Mr. Jones doing his motion, and then you graphed that motion to see what it looks like. So today we're just doing the notes to go over what you should have hopefully learned on Friday. So our I can statement today is I can interpret motion from distance time graphs. And we'll look at our first one here. We have just a distance time graph, nothing on it. We're just talking about speed, and we're defining what is speed. And so most students will tell us it's how fast something's going, but really what speed is it's how far you go in a certain amount of time. So to calculate speed, the formula would be distance divided by time. Hopefully in math, I think by now that you have worked on slope. And so when you calculate slope, there are a couple ways you can do that. You can do that with the y-intercept, which is y equals mx plus b. But another way you can do that is to look at your rise over your run, or your change in y values over your change in x values. So I have over here the slope is y2 minus y1 over x2 minus x1. And some of you might be cringing already because you're like, oh my goodness, we have to do this again. I'm not really going to make you calculate slope, but I want to point out a couple things and show you a few things. So if you're looking at your change in y's, so your y values are showing distance. If you look over here, you can see distance. Your x values are showing time. So you have distance divided by time. Notice that slope is y's over x's, which we could say is distance. Y's are distance over x's are time, which is equal to speed. So really we can say that the slope of the line is the speed of the object. So when you're looking at the slope of these graphs, you're looking at how fast it's going. Let's see if I can get this to go down here. So let's look at example 1. We have a line, but it's going straight horizontally across. So your distance is staying the same as time goes on. If your distance is not changing, that means you're staying in one place. So the object's speed here is 0 because the object isn't moving. It's staying at the same distance as time's going on. Let's look at example 2. In example 2, you just have a straight line. So here, whenever you have a straight line on a graph, you have a constant. So our object is moving forward at a constant speed. So its distance from the start is increasing. So as it's going, your distance values are getting bigger as time goes on. So you're just going ahead and moving forward at a constant speed. A straight line will equal a constant speed. Example 3, you've got a green dashed line and a solid blue line. Notice that the green dashed line gets to this distance right here and only takes this time right there. Whereas the blue line, it goes the same distance. If I take my cursor and I go across, I can see that I'm still at the same distance as green. So both made it to the same finish line, we can say. But the blue object took this long on the x-axis. So the green dashed line is indicating a faster speed because the object's traveling the same distance, but in less time. So we can conclude that a steeper slope or a bigger slope is going to equal a faster speed. Object 4 is traveling at a constant slow speed here at the beginning because my slope is not as steep, and then it changes here to a much faster constant speed. I can tell that because my slope gets steeper, which means it's going to have a bigger value, which means that my speed has a bigger value. I'm going faster. Example 5, my object starts to take off and I start going forward at a constant speed. At this point right here in the middle, notice my distance is staying the same. I'm not moving. So here I've stopped, and then I'm going back to the start again. Notice I'm not going back to the start this way. I'm not going all the way back because then I would be traveling back in time. So I need to go back to 0 on my y-axis, but I can't go back to 0 on the x because the x-axis is time. And if I went back to 0, I would be saying I'm going back in time. And I'm not. So I got to go back down the y, but I still have to be out some distance on the x. My last example is a curved line. So here I'm starting out at my start at 0, 0, and as time goes on, Notice that my y is getting faster, 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 or my slope is getting faster, 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 faster. So I am not keeping a straight line here. It's not constant. So here my speed is getting faster, faster, faster as it approaches vertical. You can go ahead and submit your notes and then use your notes to help you with the study guide. Study guide today is not due until Thursday at 11:59 because our test over graphing motion and forces in motion will be on Friday.